Well, we're now at lesson 17D. We are almost at the end. In the next preview assignment and in the next class, you will need to be able to calculate rates of change, and analyze a regression line by using R or R squared value to determine overall patterns and connections between the variables. So we're going to start with clarifying the directions for the definitions for R and R squared. In the next lesson, you will generate charts and trend lines to discuss data and assess the strength of those relationships. In previous assignment and in class activity 8D, you learned about a statistic used to measure the strength of the fit of a regression equation to the data. It was the correlation coefficient, R. Here, we're going to learn about another such statistic called the coefficient of determination, which is R squared. So question 1 asks you to review the definition of correlation coefficient, which is R, and then restate the definition in your own words. So this is a great time to hit pause, go do like questions 1, 2, and 3, and then come back and we can work through the rest of them together. So when it asks you to review the definition, you can put a whole lot of things right here, but some of the things that you could say are like the correlation coefficient tells you how strongly or how weakly the two variables vary together. The coefficient of determination is the proportion of the variation in the dependent variable that is due, some really, really important words here, that is due to the independent variable. And I would highlight, underline, it's the variation in the dependent variable that is due to the independent variable, and we call that R squared. Then it mentions that the value of R is between -1 and 1. What are the smallest and largest possible values of R squared? Well, if R is between 1 and -1, then let's play around with it and go with the lowest value. The lowest value would be -1. If we squared it, we would get a 1. Well, the highest value is a 1. If we square that, we get a 1. So then if we play with any of the pieces and parts in between and square them, we're going to notice that they keep going down, 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 down to 0, and 0 squared is 0. So what it's looking like is that we are going to be between, so R squared is either going to be less than or equal to 1, or greater than or equal to 0, or you might want to just say it is between 0 and 1 and can include 0 and 1. If you obtain R squared, will you state that the strength is very strong, weak, or very weak? And even look at this like a percentage. It's like 6.5%. And if you're looking at 0 to 100%, that's way down here at the bottom. And so it's not even halfway. It's not even up like at 75%. It's not even at 25%. So it's not very strong. It's not strong or weak. It is very weak. The coefficient of determination is very, very, very far away from 1. In addition to talking about R and R squared, you're going to need to be able to calculate rates of change. During the in-class activity 17D, you are going to explore climate change data. And you're going to create graphs and equations that display the levels of carbon dioxide in the Earth's atmosphere and corresponding temperatures. Carbon dioxide is measured in parts per million. On question 4, if you haven't already, pause, go work on question 4, and then we'll come back together. And it has 4 parts. So you can do all 4 parts or do part A and then come back and watch. But anyway, take a moment to go do at least 4A. A little bit of direction says the average rate of change between two data points is the change in one variable divided by the change in the other. It's the slope. It's the slope of the line between those 2 points, because we've seen slope as being the change in y over the change in x, and that's exactly what it's talking about. It's the change in one set of the variables divided by the change in the other. If slope is a bit rusty for you, don't forget that in your quantitative reason class, your Math 1332 class, you can go look at the resources in the very back of your book, or they're listed in my math lab, and go review, look at slope, or look at an online internet and find a resource there to explain slope. Anywhere you go, part A says the carbon dioxide concentration for the year 1959 was. And so as I'm reading this, I'm going to be thinking that if I had a date here, if I had years, because we talked about time is probably going on the x-axis, then could I have like 315 and 9700ths parts per million? Would that dot make sense? Parts per million. Well, let's see if it does. And if so, this would be an X and a Y. And then we had, for the year 1960, we had 316 and 9100ths parts per million. So this would be another Y, and here would be an X. Calculate the average rate of change in carbon dioxide concentration from 1959 to 1960. Let's round to the nearest hundredth and make sure we're using correct units. So we have some parts per million, and we have a year. So you can call it average rate of change. You can call it slope. Since we are familiar with slope, I'm going to go ahead and call it slope. And I can call this one x1, y1, and this can be our x2, y2. And here we go. I'll have 316 and 9100ths minus 315 and 9700ths. And then the year 1960, subtract the year 1959. When I do, I can subtract and divide, and let me go ahead and do that. So for my numerator, I am getting 316.91 minus 315.97 equals, I'm getting 94 hundredths in the numerator over 1. And I bet we can just say that that is going to be 94 hundredths parts per million per year. Because remember, years are on the bottom, parts per million on the top, years are in the bottom. And so the change is going to be an increase of carbon dioxide, 94 hundredths parts per million of carbon dioxide per every year. That was from, or per that year, 1959 to 1960. We're going to keep going on with B, C, and D. But D says, what do you notice about the average rate of change that you calculated? So let's keep in mind that this was the year, the years 59 to 60, and document on a separate paper or just keep it where you can see it that we were at like 94 cents, 0.94. Remember, if you haven't already hit pause and worked on B and C by yourself, go ahead and hit pause and then come back and we'll work on B and C together. I'm going to go ahead and write in the corner that we ended up with 0.94, 94 hundredths parts per million per year. And then we're going to go ahead and calculate part B. I'm going to keep in mind that we had year and parts per million. So when we go to calculate the slope, we need the change in our parts per million over the change in our years. And so this can be x1, y1, And then we've moved to 85, which is another year, so we'll call it X2. And this is another parts per million. Calculate the average rate of change from 1959 to 1985. Round, use correct units. So the way I have labeled, I'm going to end up doing 346.04 minus 315.97. And I'll do 1985 minus 1959. I'm going to grab my calculator. When I grab a calculator, I've got 346.04 minus 315.97 equals, I'm getting 30 and 700ths, written kind of crazy there. And I can punch in 1985 minus 1959, and I'm getting 26 years. When I divide 30 and 700ths by 26, and it says round to the nearest hundredth, I'm getting about 1 1600ths parts per million per every 1 year. So just a quick note, what's happening so far, we were at like 94 cents, now we're at like $1.16. Let me undo that so I can see the number below, and I can go ahead and mark it there. So we've gone up, we didn't stay the same, but let's see what happens in this last one. So then on part D, we can ask or answer, what are we noticing about these average or the average rates of change? So finally, part C says, here's another year, here is another carbon dioxide reading, here is another year, and here is another carbon dioxide reading. So we're going to calculate our slope as, that needs to say Y1. And X1. And we're going to take our Y2, subtract our Y1, and then take our X2, subtract our X1, grab a calculator, and do 396 and 4700ths minus 315 and 97 hundredths. And I'm getting 80 and 5/10. I'll do 2013 minus 1959, and I'm getting 54 years. And when I do 80 and 5/10 and divide it by 54, rounding to the nearest hundredth, I'm getting about 1 49 parts per million per 1 year. So in part D, to answer their question about what do we notice about the average rates of change, we started up here with 0.94, moved up to $1.16, and now we're at 1 49 parts per million per year. So to answer part D, the average rates of change are increasing. We are finished with lesson 17D. You need to look at your syllabus and see if you have more lessons for this week. And if you do, keep going. If you don't, do that happy dance, and we'll see you on some videos later. Bye-bye.